Hi, everyone, and welcome to another seminar of Physics Latam. And today we have the fourth lecture in Supersymmetry with Professor Silvia Penati. Please go ahead, Professor.
Thank you very much. So welcome to the fourth lecture. Okay, so we will keep going from what we were doing yesterday. And in fact, I reported here what we were considering as the starting algebra, what we call the n=1 supersymmetry algebra. Because, and remember yesterday, what we did was to study and construct in a systematic way representations of this algebra. And we argued somehow that we can organize particles, elementary particles, into representations of supersymmetry algebra, which, remember, are what we call supermultiplets. And most important thing to keep in mind is that these representations are finite representations that contain a finite number of particles. Let me scroll down, because actually the n=1 supersymmetry algebra contains, remember, also an R-symmetry generator that for n=1 supersymmetry is a U1 R-symmetry. Okay, which acts non-trivially on the supercharges Q and Q bar. And in fact, under these transformations, you can realize that the rest of the commutators and anti-commutators are invariant. Okay, so what we would like to do today is to give brief introductions to extended supersymmetry. So we will go through it a little bit, but as I told you already at the starting point of the course, when I was just giving you the plan of the course, then we will go back to n=1 to start, to do some physical application and start studying some interesting physical theory. Okay, so, but for today, I think we can spend some time introducing an extended supersymmetry algebra. So let me write an extended algebra. Okay, so the idea is very simple. And it goes as follows. Remember that in order to construct n=1 supersymmetry, we introduced basically one Majorana spinor made by, of generators made by Q alpha and Q bar alpha dot as the two by components. Nothing prevents me by introducing more than one Majorana spinor. Okay, so what we can do is we generalize the previous construction by introducing n Majorana spinors of generators that we write this way. So we will have the Q alpha I, and let me just stick to my conventions. Q bar alpha dot J, sorry, I, this is still I. Okay, with I from 1 to n. So this label I counts the number of Majorana spinors that I'm introducing, and we take I to be an index in the fundamental representation of SUN. Fundamental representation of SUN. Okay, so it means that this n Majorana spinors transform among themselves through the action of SUN generators. Okay, so how do we generalize the previous algebra? Remember, the previous algebra was built by the usual Poincare algebra, this does not change. Of course, we will keep the same kind of commutator, so forget about the Poincare part. Let's focus on the, let's say, new part, which involves the supersymmetry charges. So let's see what happens to the first 3 lines. Okay, so I can write the most general structure for instance, for the first line of anti-commutators, which now goes as follows. So we set up anti-commutators as follows. If we anti-commute Q alpha I with the Q bar alpha dot J. Sorry, this has to be down. Remember, in the previous case, we simply had 2P alpha alpha dot. I will add here delta IJ. Means that basically the N Majorana spinors satisfy the same kind of anti-commutator separately. However, in this case, if I consider the anti-commutator of 2Q, in the previous case, we were forced to set this anti-commutator equal to 0 because of what? Because we didn't have any possible anti-symmetry structure to build up a non-vanishing right-hand side. In this case, having 2 extra indices, I and J, I can certainly build up something non-vanishing on the right-hand side, which has the following form. Concerning the alpha beta indices, the spinorial indices, I can introduce the usual epsilon alpha beta, and then I multiply by Zij, asking, of course, that Zij is an anti-symmetric tensor in the SUN indices. Okay. This is, of course, due to the fact that the left-hand side is anti-symmetric. Sorry, is symmetric. So you have to multiply two anti-symmetric tensors. This is Z, and of course, I can also do the same for Q bar. This will be equal to some Z bar IJ, okay, with the same condition. Okay, these Z are called the central charges. This one and this one are central charges. Okay, so as you can see, if I introduce more than one supersymmetry, and since here we introduce n Majorana spinors of generators, we will call it n extended supersymmetry. We have the freedom to generalize a little bit the structure of the anti-commutators. This is not the end of the story, because then together with the original original algebra and the correct generalization of the original algebra, I have also to take care of the algebra of the internal indices I, the indices of the SUN group. And in fact, we will have to introduce, so moreover, we introduce SUN generators, okay, in the fundamental representation. Therefore, we will write that we can deal with some matrices Tij, which by definition is a linear combination of the SUN generators with matrix entries I and J. Okay. Good. So these generators act non-trivially on what? They act non-trivially on the spinorial generators, of course, because they carry an high index, and they work non-trivially on the central charges because they also carry SUN indices, okay? If you are a little bit patient, I can write for you the correct commutators that we should include in our algebra. Therefore, we can write something like Tij commutator with the Q alpha K. This is minus I delta JK Q alpha I minus 1 over N delta IJ Q alpha K. The same for Q bar. So Tij Q bar alpha dot K. This is will be equal to I delta IK Q bar alpha dot J minus 1 over N delta IJ Q bar alpha dot K. Then, of course, as I said, we have a non-trivial action of these generators on the central charges, which let me call it KL. This is minus I delta JK ZIL plus delta JL Z KI minus 2 over N delta IJ Z KL. This is the action on Z. Of course, and then you have to give the algebra of the SUN algebra. This is in this notation, this is delta IL TJK minus delta JK TIL. Okay. So you have to put together at this point this set of anti-commutation relations together with this set, together with the ordinary Poincaré part, so the commutators for P and M. And remember that we also have a U1R symmetry. U1R symmetry is trivially generalized. Now we simply have to act not only on single Majorana, but on every single Majorana. So this will have charge plus, the Q bar, they have charge minus. Okay. And that's it. Okay, so the algebra is a little bit more complicated, but of course it closes in the sense that it respects the Jacobi identities. Moreover, it's nice that having introduced an extra I index here, which is an SUN fundamental index, basically I managed to include in the algebra also the generators of sort of internal symmetry, okay, which is what we were dealing also in the novel theorem of Coleman-Mandula. But you see now T talk non-trivially to the rest of the algebra through Q, therefore this is a sort of experimental proof that we managed to go around the restrictions given by the novel theorem by Coleman-Mandula. Okay, now for this more general case, we will like to go to what we did yesterday, constructing now massive and massless representations for this more general supersymmetry algebra. Okay, hope everything is clear. I have, okay, let me say that I have the hidden convention that whatever is not written explicitly, so if I do not write explicitly here some commutator or some anti-commutator, it means that they are zero. Okay. For instance, I didn't write any commutator or anti-commutator of the central charges with the rest of the generators, because except for T, because all they are all zero. So Zij commutes with all the Qs and all the Poincare generators. That's why I'm not taking care of these extra commutators. Okay, so if we follow the same logic that we used yesterday, we will start by studying massive representations. So let me also write the representations of an extended SUSY algebra. And as we did yesterday, we start with massive representations. I can go a little bit faster than yesterday because, you know, kind of a technique and kind of logic I'm going to apply today is exactly the same, except that now we have to deal with more than one Majorana spinor of generators. First of all, let me say that we will set for simplicity all the central charges equal to zero. This is consistent because, as I said, the central charges commute with everything. Okay, just to make our life simpler. Now, if I consider, as we did already in the n equal to 1 case, the main anti-commutation relation from which I can grasp all the information about representation, which is this one. Okay, notice that I set the central charges equal to zero, so I'm back to a situation much more similar to what we had yesterday with QQ and Q bar anti-commute. Okay, but we still have this non-trivial anti-commutator. But I can split, you know, since there is a delta here, it means that I have one algebra QQ bar when I is equal to 1, one when I is equal to 2. So basically I have a replica of n identical algebras, correct? So we start from Q alpha I, Q bar alpha dot J equal twice delta Ij P alpha alpha dot. So this time we have 2n replicas of Clifford algebras when we go to the rest frame. Remember that which means that we consider this one. In fact, if you proceed exactly as we did yesterday, you will find that Q alpha I, Q bar alpha dot J is equal to 2m delta Ij. Then you can even want, sorry, a delta alpha beta. As a delta alpha dot. Then you may want to rescale Q and Q bar by square root of 2n in order to generate exactly the Clifford algebra. But basically, this is the starting point. Okay, so how do I proceed in this case? Remember that Q and Q bar can be identified with annihilation and creation operators for spin, respectively. Therefore, I can define a Clifford vacuum, which is annihilated this time by all the Qs. So we define the Clifford vacuum, which, remember, yesterday sorry, this is MS3. Yesterday was defined by this condition for alpha equal to 1 and 2. Now, remember, alpha carries an index I, an SUN index, so I will impose the same condition for any entry Q1, Q2, Q3, Qn. So I going from 1 to n. Okay. Good. At this point, starting from the Clifford vacuum, I have the possibility to build up the whole multiplet by applying Q bars. How many Q bars this time? So we can construct the whole representation, which is what we call the supermultiplet, by acting with the Q bar alpha dot I, when alpha dot can be 1 dot or 2 dot, and I, as I said, can go from 1 to n. So in total, I can act on the Clifford vacuum with 2n generators. Okay. Okay, so you can understand that now I have a much more freedom. I have many more creation operators to build up exact states, and then I expect my multiplet, my representation, to be definitely longer compared to what we had yesterday. In fact, let's see what happens. So yeah, I can write, well, let's change. Let's go here. As we did yesterday, I can write the state, the spin, and the number of components. Okay, let's start with the initial state, which is a state as spin S, and therefore we have 2S plus 1 components. Okay, let me write, you will understand in a while why I'm doing that. Let me, here we have 1. Let me write this 1 as 2n 0 binomial. Okay. Now, at the next step, we can construct something applying Q bar alpha dot I to M as S3. Okay. As we know, then you have to combine the angular momentum. So this state brings spin S, Q bar brings spin per half. Therefore, we will have 2 possible spin states, S plus 1/2 and S minus 1. How many states? Of course, because of the degeneracy in S3, we still have 2S plus 1, but how many? This time we have I going from 1 to n and alpha dot 1 and 2, so I have 2n possible states. Let me write 2n as 2n over 1. Okay. And the other nice observation is that now when you act on a state with some Q, the state, the new state will carry an extra quantum number, which is an SUN quantum number, of course, the I. Correct? So this new state will be in a fundamental representation of SUN. Together with being, you know, in a representation, particular representation of a Poincare group, and blah, blah, blah. Good. Then I can go on. Now I can apply Q bar beta dot J to Q bar alpha dot I M S S3. This time, remember, I and J can go from 1 to n both. Alpha dot and beta dot can be 1 and 2. The number, well, let's first of all write the spin. Now the spin can be S plus 1, S and S minus 1. Okay, we have a degeneracy, which is 2S plus 1. But how many states? The states, have, when you count the states, you have to take into account that this expression is anti-symmetric in the exchange of alpha dot I and beta dot J, because of course the Q bar anti-commute. Therefore, the number of states will be 2n times 2n minus 1 over 2, which is the number of anti-symmetric structures that you can construct with two Q bars. Okay, so the number should be 2n times 2n minus 1 over 2, that I write as n over 2. Okay. Then you go on, depending on how large is your n, you can go on for a while, up to a situation where now you apply, let me call Q alpha 1, Q bar alpha dot 2, Q bar alpha dot n. So you apply all the Q's to M S S3. Okay. Which is the maximum spin that you obtain in this case. It will be S plus n over 2 when all the Q's contribute with the plus 1/2. But then you have, as a second stage, you have S plus n over 2 minus 1, and then so and so forth, up to S minus n over 2. So you have a larger spectrum of spins. And how many states? The usual degeneracy times, I don't know what's going on here. How many states? The states now are basically n, so you have 2n over n states. At this point, look what happens. Basically, you have solved all possible, so you have used all possible Q bars from the point of view of the I index, because you have 1 to n, but you still have the freedom of acting with some Q bar with the same I index, but different alpha dot index. Okay, so for instance, if this is Q 1 dot 1 bar, you can act with the Q bar 2 dot 1, because this is not 0, correct? But remember, if I put these two things together, let me write better. Q bar 1 dot 1, this is nothing but Q bar 1 in the sense of the I index square. But this is a scalar. So when you start applying extra Q bars, you go down in the number of Q bars acting on the initial state. So you will start decreasing the spin. Okay. Spin starts decreasing. up to the final possible state that you can construct, which is the one where you act with all the q bars, which is this one, q bar 1 square, q bar 2 square, q bar n square applied to m s s3, which is back to speed s. The number of states is back to be 1, but let me write this one as 2n over 2n. It's just convenience. Okay. Okay, so first of all, I hope I managed to convince you that, of course, more q bar you have, more states you can generate. Second, you know, by the usual rule for momentum, the angular momentum summation, you see that if you start from a Clifford state which has a spin s, and you are dealing with max n extended supersymmetry, the maximal spin that you can generate in your representation is s plus n over 2. Okay, so let's say the spread of the spin is between s plus n over 2. Okay. Moreover, what I can do at this point is easily computing the dimension of this representation. How do I compute the dimension of this representation? Now you will understand why I wrote these ones in this kind of fancy way, because now the dimension is basically 2s plus 1 times the sum for k from 0 to 2n of 2n over k. Do you agree? Well, you have to figure out what happens here, but probably with a little thinking, you will agree with me. Okay, but this is 2s plus 1. This is nothing but the expansion of the Newton binomial. So this is simply 2 power to n. This is the expansion of 1 plus 1 power to n, which is 2 power to n. Of course, when I build up the representations in the n extended case, I have to check time by time that when I set n equal to 1, I go back to what I obtained yesterday. In fact, if I now set n equal to 1, remember, I do get 2 power 2, which is 4, times 2s plus 1. And in fact, this is the dimension of the massive representation that we found yesterday with the spin s. Okay, there is another interesting observation, which is the following. If you consider the binomial expansion of 1 minus 1 power to n, not 1 plus 1, this is, of course, 0, 1 minus 1. But if you close your eyes and you just use the expansion, this will be equal to sum for k from 0 to 2n k times minus 1 power k. Okay, but then you can split the sum between k even and k odd. So you will get the first sum from 0 to n of 2n over 2k. Now, if k is even, of course, this is 1, but when k is odd, this is minus 1, so that minus the sum for k from 0 to n over 2k plus 1. Okay, so what I read here is that, you know, the number of, well, now depends on the spin, the number of even states or odd is equal to the number of odd or even, depending whether your original Clifford vacuum is even or not, or odd. in fact, every 2 steps you reproduce. If you start with even, every 2 steps you reproduce even, whereas you know at 1, 3, 5, 7 steps you produce odd spins. So once again, even in the understanding algebra, I realized that in a very simple way that the number of even states equals the number of odd states, or if you wish, the number of bosons in a representation of understanding algebra equals the number of fermions. So this is bosons. Number of bosons equal to number of fermions. Okay. I can play the same game now, but more or less the same game in the massless case. Let me see if I want first to give you some, not really. No, okay. You can enjoy yourself. You can do it as an exercise. For instance, trying to construct the simplest representations. For instance, the one for s equal to 0, the one for s equal to 1/2 and 1. These are the simplest representations that you can build up. Okay, so we can move to the massless case, massless representations. Okay, remember that in this case, what I do is to go to the standard frame, which means setting p mu equal to this 4 vector. Okay, remember how things work for n equal to 1, for n standard, there is, sorry, let me see if I have to answer now. No, there are no questions. Okay, if you play the same game that we did, yeah, we played yesterday, of course, now reproduced n times, what we will get is q 1 I q bar 1 dot j equal to 4e delta ij. If you remove I and j, this is exactly what we had yesterday, and q2i q bar 2 dot j equal to 0, plus the fact that q1 and q2 anti-commute. Okay, so in this case, what we have is n replicas of Clifford algebras. Okay, 1 for each I, of course. Okay, so we can proceed in constructing the corresponding representations, massless representations, by define. So we define the Clifford vacuum given by Q1I. To remember that in this case, I have to label my states with 2 quantum numbers, which are the energy and the helicity. So this has to be 0 for any I from 1 to n. And of course, Q2I and Q bar 2 dot I equal to 0. Okay, so now starting from this Clifford vacuum, E lambda 0, I will build up the whole representation. So this is still classified in this way. So we have the state, helicity, a number of components, Okay, so the first one is the cliff for vacuum, which has helicity lambda 0. How many states do we have? Just one. Let me write this one as n over 0. Then I can apply q bar 1 dot I. And what we find is, of course, that the helicity gets increased by 1/2 due to q bar, and the number of states. How many states do we have this time? 1 for each I, so we do have n states, which I write as n over 1. And as I said already, for the massive case, this will give you a new state which carries also an SUN fundamental index. Okay, and next step, I can apply another U1, yes, 1 dot, this time J. J has to be different from I, of course, otherwise you get 0. You increase the helicity by 1/2. This state has to be antisymmetric in the exchange of I and J. Therefore, the number of components will be n times n minus 1 over 2, which is n over 2. Okay, then you proceed applying another q bar, blah, 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 up to which point? Up to the point where you have applied all the q bars. And applying all the q bars means that you end up with q bar 1.1, q bar 1.2, q bar 1.n applied to E lambda 0. And in this case, you will have increased the helicity by n over 2. And the number of states is that to be 1 that I write as n over n. Okay, so even in the massless case, well, this kind of trivial observation, you have, of course, that depending on how long, so depending on how, depending on the value of n, so what is the degree of extension of your supersymmetry, you have longer and longer multiplets. Okay, and again, if I start with the helicity lambda 0, the maximal helicity that I can produce is lambda 0 plus 1/2. Sorry, plus n over 2. Okay, so we can compute the dimension of the representation. The dimension of the representation is given by the sum for k from 0 to n over k. Okay, which is 1 plus 1 power n, so this is 2 power n. This is the dimension. And in fact, remember, if you set n equal to 1, you are back to the representation, the massless representation of n equal 1 superalgebra, that in fact it was, we found yesterday it was 2. And you can still play with the fact that 1 minus 1 power n can be written as the sum, which is 0, of course. Can be written as the sum from k from 0 to the integer part of n over 2 of n over 2k minus the same summation of n over 2k plus 1. So basically what we find is that the number of even helicities equal or odd equal the number of odd helicities or even, depending which is the value of the helicity you start with. Okay, even in this case, I have to comment about CPT invariance of my theory. This is something that I commented already yesterday, but let me give you a few more details because I got a question yesterday about CPT. So there is, I don't know if you know, but there is, let's call it problem of CPT invariance. If probably you know that, but if you don't, I'm going to tell you. There is a general theorem according to which any relativistic local quantum field theory has to be CPT invariant. You know, CPT is what? C is charge conjugation that we also introduced the first lecture. P is parity transformation, which means that I'm going to send the spatial coordinates to minus x, and t is time reversal. Which means that I'm considering this discrete transformation S0 going into minus x0. So what we know is that in nature, there are interactions, in particular interactions which involve weak interactions that may not respect P and C, but in any case, I mean, we have never observed any physical effect where CPT is violated. So CPT is experimentally not violated. And we do also have theoretical proof that, quantum field theory under suitable and reasonable assumptions has to be CPT invariant. Okay, so in particular, the Hilbert space of your states, the spectrum of your states has to be CPT invariant. Okay, so any quantum field theory, which is a relativistic local theory, is CPT invariant. Okay, therefore, the spectrum of states has to be CPT invariant. Good. However, it's clear, remember that when we define the helicity operator, we introduced this yesterday. This is nothing but, forget about the D1 over E, this is nothing but the scalar product between the angular momentum, the special angular momentum, and the special momentum. If you perform a CPT, particular PT transformation on this operator, it's easy to understand that under PT, this goes to minus gamma. So in particular, the spectrum of eigenvalues for this operator change sign under CPT transformation. Okay. In particular, helicity, eigenvalues, change sign under CPT. Okay, but this means that if the spectrum of states has to be CPT invariant, this is equivalent to say that the whole spectrum of states, so my Hilbert states, has to contain, for any E lambda state, the corresponding E minus lambda state. Otherwise, you break CPT. Okay. What we observed already yesterday in the n=1 case, and that I can observe even here for the n-standard case, it may be that this spectrum of elicities that are contained in a representation, which go from lambda 0 to lambda 0 plus n/2, is not symmetric respect to 0, does not contain lambda 0 plus 1/2, blah, 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 up to minus lambda 0, correct? Remember, for instance, when we were dealing with n=1 yesterday, the spectrum of elicities are lambda 0 and lambda 0 plus 1/2. It does not contain minus lambda 0. It does not contain minus lambda 0 minus 1/2. However, in my Hilbert space, I do have these states because of CPT invariance. Okay. Therefore, I have to organize my states in terms of supersymmetry representations, keeping in mind that for each representation, I will have the corresponding CPT conjugate representation. And in order to build up a representation which is invariant under CPT transformations, I have always to put together the representation plus the CPT conjugate. That's the question that I was trying to address yesterday, okay? So in particular, consider, for instance, the case, consider representations for, sorry, let me say massless representations for n=1 case. Remember, we had this representation, but as I said, of course, that my Hilbert space has to contain also E minus lambda minus 1/2 and E minus lambda. And what I can simply prove is that I can reorganize these other two states in the conjugate, in the CPT conjugate representation of supersymmetry. Representation. And in order to have a CPT invariant spectrum over supersymmetry representations, I have to consider the two of them together, okay? The same thing here for the n-standard case. So in the n-standard case, the multiplet that we have built up is E lambda 0, E lambda 0 plus 1/2, blah, 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 up to E lambda 0 plus n/2. This is a longer, definitely longer multiplet, so it might be that it is a self-CPT conjugate. Why and when this may happen? So this can be CPT self-conjugate, which means that it contains already all the spectrum between the minus plus the maximal value of the helicity. So when lambda 0 plus n/2 is equal to minus lambda 0. Do you agree? Because in this way, I would go from lambda 0 up to minus lambda 0 or vice versa. Is that something that may happen? Well, if you solve this simple equation, you will get that this happens. This is equivalent to say that lambda 0 is equal to minus n/4. Okay, so the conclusion is that for lambda 0 equal to minus n/4, the massless representation is CPT self conjugate. Okay, and I have to consider only the representation itself. If this is not the case, the representation that I build up is not CPT self-conjugate. Therefore, what I have to consider is the representation plus the corresponding CPT conjugate, which is the one which all the negative values. So the opposite, not negative, that could be already negative. The opposite value of the elicities. Okay. There are, so this is kind of important. In fact, there are two remarkable situations where this does happen. Situations where lambda 0, in fact, is equal to minus n over 4. The first case is when you choose n equal to 4. If you ever heard about n equal to 4 superharmonious, and now we start getting some familiarity with n equal to 4. So this means having n equal to 4 extended supersymmetry. And if you choose n equal to 4, you will find that lambda 0 is equal to minus 1. And in fact, this is a kind of multiplet that I can build up. Density and number of components. You start with the helicity minus 1. Then remember, you go up minus 1 plus 1/2, which is minus 1/2. And then you add again 1/2, so you get 0. Plus 1/2, you get 1/2. Plus 1/2, you get 1. And in fact, this is self-conjugate in the sense that the helicities goes from minus 1 to 1. And the number of components, you can make the exercise to check that what I'm going to write is correct. 4, 1. Okay. And the other, but notice that here we have, this is important, n equal to 4. The other remarkable situation is when you choose n equal to 8. Therefore, for n equal to 8, lambda 0 over here is minus 2. Okay, this time the multiplet starts with helicity minus 2, then you add 1/2 and you get minus 3/2, then you get minus 1, minus 1/2, 0, and then you start 1/2, 1, 3/2, 2, and the number of components are 1, 8, this is 28, and then so forth, up to 1 here. Okay, and it's remarkable that this happens for n equal to 8. Okay, so if we think that self-conjugate multiplets can play a role, or maybe they can be more interesting, I realized that, of course, they arise when we consider 4 extended supersymmetry or n equal to 8 extended supersymmetry. In particular, the self-conjugate multiplet in the n equal to 4 case contains spin 1, 1/2, and 0. But remember, 1/2 is matter, 1 is, basically vector fields, 0 are scalars. And whereas for n equal to 8, the helicity goes from minus 2 to 2. So we have particles with helicity 2, 3/2, 1, 1/2, 0, and the opposite. Okay, but I have a final observation concerning n equal to 4 and n equal to 8. If you think about it for a moment, if you were to higher the degree of supersymmetry, in this case, getting to n equal to 5, n equal to 6, you would increase the helicity. Well, for massless particles, helicity is look like a spin, okay? We would have spin higher, helicity higher than 1, but there is a general statement based basically on many different considerations, which is the following. In quantum field theories without gravity, there is no consistent way to have propagating particles with spin or helicity greater than 1. Okay, so 1 is the maximal value of helicity or spin that you can have for a particle if you want to write down a consistent quantum field theory describing interactions. Okay, this means that n equal to 4, as I shown here, is the maximal amount of supersymmetry that you can have. Of course, we are in 4 dimensions without gravity. So the maximal amount of supersymmetry that you may want to include in your quantum field theory is n equal to 4. N equal to 4 is the maximal amount of SUSY in 4D quantum field theory with no gravity. Okay. There is a second part of the statement, which is the following: in quantum field theory with gravity, there is no consistent way to propagate particles with spin greater than 2. Okay, therefore, from the construction that we have here, or in the massive case, the maximal amount of supersymmetry that you can have in 4 dimensions in the presence of gravity is n equal to 8. So n equal to 8 is the maximal amount of SUSY in 4-dimensional quantum field theory with gravity. Okay, this is something that you should remember for the rest of your life. Okay. Okay, let me see if I have more comments on the construction. Yes, I have one last comment, and then we can stop for a break. The last comment concerns the central charges. You might ask me, and probably you want to ask me, okay, you did the construction setting the central charges equal to 0 to begin with, just to make the life easier. What happens if now we turn on the central charges? So representations in the presence of central charges. Remember that I call Z ij and Z bar ij. Okay. What happens is the following. I'm just telling you what happens, but we are not going to do anything. If you want to read a very detailed construction, have a look at Sonius. Okay, let me just mention that in the massless case, there is no way. Massless case always requires the central charges equal to 0. You cannot construct massless representations in the presence of central charges. However, in the massive case, you can. What you have to use is the fact that, well, basically, again, as follows from the algebra. This is still some sort of information that you can simply get from the algebra. If you turn on the central charge has to be always less or equal to m or to m, depends on your conventions. But the point is that there is a constraint. So the central charge has to be constrained. Okay. This is what we call the BPS constraints. Okay, so what happens is that if the central charge is corresponding to your Q's, they all are, let's say, if all Q bars satisfy Z strictly less of that as M, the construction is equal to the previous one. No change in the construction. Instead, if some Q bars satisfy the corresponding Z to be equal to M, then what happens is that you have a shortening in the representation. The corresponding representation is shorter in the sense that it contains a less number of components. We have a shortening of the representation. And in fact, we will call it short representation. It may happen that for all the Qs, we have the BPS constraint is satisfied. So in this case, BPS bound satisfied by all Q bars. In that case, we have an even shortening of the representation. And in fact, in this case, you have the shortest possible representation that you can build up. In fact, these are called ultra short multiplets or representations. Okay, when this happens, we say that the BPS bound is is satisfied by all the Q bars. And we have ultra short. It's basically, you saturate the bound for all the Q bars, and this is what happens. Okay, I think we can have a break now. Ready? Okay, so what I'm going to do now is to somehow merge what we have done at the very beginning when you remember we constructed some supersymmetry generators starting from scratch, basically starting from a very simple theory written in terms of local fields, a scalar and a spinor. And what we have been doing now in a more formal way, starting directly from the algebra and constructing representations. So the merging goes, of course, through the explicit realization in terms of fields of my representations. In order to do that, we will go back to the n=1 case. So basically, this part concludes my detour through the n-standard for the time being. Then, if I have time, I will come back to n=4 at least in one of my last lectures. But for the time being, I will restrict to n=1. So let's go back to n=1 SUSY. And what I want to do is to construct a field representation, realization of supermultiplets. Okay, so let me recall what we did, I think, in the second lecture. Remember that we were considering a very simple action for one complex scalar and a Majorana fermion. And we wrote this thing. Okay, but then remember, in order to close the algebra of shell, we introduced also the auxiliary fields F and F bar. Okay, remember that we proved that this action is invariant under transformations, SUSY transformations, that we wrote this way. If phi, big phi stands for any of the fields, this is by definition I epsilon alpha Q alpha plus epsilon bar alpha dot Q bar alpha dot phi. And we found the explicit realization, the explicit action of Q and Q bar on the two fields, the small phi and the psi. And in fact, sorry, but I have to write it again. Otherwise, we don't make a match. So what we wrote at that time is that Q alpha acting on phi, so this is equal to I psi alpha, whereas Q bar alpha dot acting on phi is equal to 0. Then we found that Q bar alpha dot acting on phi bar is equal to I psi bar alpha dot, and Q alpha acting on phi bar is equal to 0. Q alpha psi beta was equal to minus epsilon alpha beta F, and similarly Q bar alpha dot psi bar beta dot equal to I epsilon alpha dot beta dot F bar. Okay, then we have the Q bar alpha dot psi beta equal to 2 d beta alpha dot phi. Q alpha psi bar beta dot equal to 2d alpha beta dot phi bar. Almost done. Q alpha F equal to 0. Q bar alpha dot F bar equal to 0. Q bar alpha dot F equal to minus 2d alpha alpha dot psi alpha, and Q alpha F bar equal to minus 2d alpha alpha dot psi bar alpha dot. Okay. How do I match these kind of transformations with what we did in the constructions of representations? Well, just remember that in the state field, the state field correspondence, we can think of our Clifford vacua as obtained by acting with local fields on the true vacuum that we call 0. And of course, we also assume that supersymmetry is preserved at quantum level. So there is no spontaneous supersymmetry breaking, which means that, of course, the vacuum has to satisfy these conditions. Okay, very good. So let's start with the following state. So what I want to do now is to use basically the same technique that we used in the formal constructions of representations, but when the states are now realized explicitly using local fields, okay? In particular, take into account, because this is going to be important, that we have these two, I would say, sort of constraints, okay, that will become very useful in what we are going to do. In fact, so consider the state, let me call it phi bar, obtained by applying phi bar to the vacuum. This is a state which has a spin 0. Okay, so it should correspond to, if it is a Clifford vacuum, I can use it to construct a representation corresponding to the initial state with the spin equal to 0. The question is, can I use this as a Clifford state? Is it a Clifford state? A Clifford vacuum. Remember that the Clifford vacuum has to be killed by Q. Okay, let's try to see what happens if I apply Q to this state. This is Q alpha. Let's do it step by step. Q alpha phi bar X, the vacuum. Since the vacuum is Q invariant, I'm going to use this strong condition. This can be rewritten as Q alpha phi bar applied to 0, but that's why this becomes important. Look, Q alpha commutator with phi bar is equal to 0. Okay, so let me give this a number. This is another number. Okay. Okay, therefore this is indeed 0 using constraint 2. Sorry, it was 1, of course. Constraint 1. Very good. So this, I can use phi bar as the lowest component of the multiplet that I'm going to construct applying Q bar. Okay, so now the next step, so let me do already as we were doing, state, spin, number of components. Okay, so the initial state is this phi bar. It has a spin equal to 0, and we have one state. Then what I can do is to apply Q bar alpha dot to phi bar. Okay. This is something that I'm going to do down here because I have to do some little calculation. So this is q bar alpha dot times phi bar x applied to 0. Okay, but once again, using that q bar kills the vacuum, I can write this as the commutator applied to 0, but the commutator is what? I go back here, you see the commutator is I psi bar alpha dot. So this is nothing but I psi bar alpha dot x applied to 0. So this is, okay, we can call it psi bar alpha dot, of course. Okay, it has a spin 1/2, and we will have two components because alpha dot can be 1 dot and 2 dot. Then I will keep going. I will apply q bar beta dot to q bar alpha dot to phi bar. Okay, but remember this is proportional to epsilon alpha dot beta dot q bar square phi bar. So let's see what happens. I will do the little calculation down here. Okay, so this was this one, and this is this calculation. Okay, so this is a q bar beta dot applied to q bar alpha dot phi bar, but I know already that q bar alpha dot phi bar is I psi bar alpha dot x the vacuum. So this is equal to I, the anti-commutator of q bar alpha dot, sorry, beta dot, with psi bar alpha dot x applied to the vacuum. Okay, at this point I go back. Q bar alpha dot psi bar is written here. Up to some I, whatever, it is proportional to f bar. Okay, so this is proportional to f bar of x 0. So what I get here is eventually something which is, let me call it f bar. Okay, this has again spin 0 and 1 component. Very good. So in terms of, rather than now, let's say, rather than talking about states, I can directly talk about fields. Therefore, I start with the fields phi bar x. I produce the psi bar alpha dot x, and eventually I produce f bar x. Okay. Therefore, in terms of fields, the representation is given by the multiplet phi bar x, psi bar alpha dot x, f bar x. Okay, this is in fact what we call the anti-chiral multiplet. Well, you can ask yourself why anti-chiral. Well, I would say because, you know, it contains one complex scalar, another complex scalar, which is indeed a pseudoscalar, but in any case, these are scalars, and the anti-chiral component of a Majorana spinor. That's why we call this multiplet anti-chiral multiplet. Remember that the construction of this multiplet relies on the fact that to begin with, we had this constraint. And in fact, this constraint is what we call the anti-chiral constraint. Okay, so let me say it relies on the anti-chiral constraint, which is Q alpha phi bar x equal to 0. Okay, but we have, hopefully everything is clear. We have another constraint which involves phi rather than phi bar. Basically, you can redo whatever what we have done, just taking the complex conjugate. So if we start with another, let's say similarly, if we start from the, what we would call now chiral constraint, Q bar alpha dot phi of x equal to 0, we can build up another representation starting from another Clifford vacuum. So we can construct another Clifford vacuum, this time given by phi of x acting on the vacuum of the theory, which is killed by Q bar alpha dot. Okay, therefore, in this case, you can use, instead of using now Q bar to increase the spin, we can build up the whole representation using Q. Okay, now the representation will be given by phi, the state phi, the Q alpha phi, which will be proportional to a state psi alpha, and Q squared phi, which will be proportional to F. Okay, still with spin 0, 1/2, 0. Okay, therefore, in terms of fields, this representation corresponds to the multiplet phi of x, psi alpha of x, f of x, okay? And of course, consistently what we have done, this is what we call the chiral multiplet. Okay, this is a way, this is, well, the simplest situation that we can consider, but what I wanted to stress is that, you know, you can talk about representations either organizing directly states of your Hilbert space or organizing fields, local fields that, you know, when acting on the vacuum of the theory, produce the states. We, of course, since we will be dealing with quantum field theories written in terms of Lagrangians, which are given in terms of local fields, we will prefer to talk about representations realized in terms of field multiplets. So this is our language from now on. Okay. Of course, if you put together the chiral multiplet and the anti-chiral multiplet, if we consider chiral plus anti-chiral multiplets, we are describing what? We are putting together phi psi alpha f plus phi bar alpha dot f bar. So what we are describing are one complex scalar given by phi bar, 1 Majorana spinor given by psi bar alpha dot, and 1 complex. This is a scalar, but actually it's a pseudo scalar. You know what I mean? It's a scalar from Lorentz point of view. It's a scalar, but under parity, it transforms it with the opposite sign. And this is given by, oops, this is given by F bar. Okay. The construction of chiral and anti-chiral multiplets is definitely not the most general irreducible representation that I can construct. Sorry, not irreducible, I take it back. It's not the most general representation that you can construct. In fact, this should be kind of intuitive, because remember, these two representations rely on the two constraints, the chiral and the anti-chiral constraints. Therefore, they are sort of constrained representations. If I relax any kind of constraint, I would expect to find, a representation which is definitely longer. Longer means which contains a higher number of components. In fact, the most general representation that I can write down, the most general multiplet for n equal to 1, multiplet for n equal to 1 is a real multiplet that I call V. This is what we call the scalar multiplet, and these are the components that I can find out applying, so basically supersymmetry transformations. I will tell you in a moment which are these fields. M, N, A mu, lambda, and D. Okay, this is what we call the scalar multiplet. Okay, so remember, for n equal to 1, we have a chiral multiplet, the anti-chiral multiplet, the scalar multiplet, which are, what are these components? So this is, let's see if I can do something clever. This and this are pseudo scalars. Okay, and let me change color. Then we have chi and lambda. They are Majorana spinors. Okay, then we have a mu, which is vector field. Sorry, even n is also pseudoscalar. So also n is pseudoscalar, and finally m is a real scalar. Okay. To be complete, you know, this information is not enough. I have to tell you how the different components transform under supersymmetry transformations. And this is the way we write the supersymmetry transformation of these components. So I start with the first one, delta C. If, as usual, I'm going to write the SUSY transformations in terms of epsilon bar parameter, okay? So this is epsilon bar, gamma phi, chi. If you transform chi, this is m plus gamma phi n epsilon. minus I gamma mu, A mu plus gamma 5 d mu C epsilon. Delta n is equal to epsilon bar. I'm going to give you all these details because then you can do some exercise. Delta n is equal to epsilon bar, gamma 5, lambda minus I d slash chi. Delta A mu is equal to I epsilon bar, gamma mu lambda plus epsilon d mu chi. Almost done. Delta lambda minus I gamma mu nu epsilon d mu A nu minus gamma 5 epsilon d. And delta d is equal to minus I epsilon bar d slash gamma 5 lambda. Okay, you may find sort of different transformation with different coefficients because of, they of course depend on the conventions. Here I'm using Sonius conventions. Okay. What is the exercise that I would like you to do is the following. You can see that this multiplet is a reducible representation. This is probably the first time we meet a reducible representation, because in fact there are a subset of fields which transform among themselves and do not talk to the rest. Okay, let's see how we can figure it out. So this is a reducible representation because it contains two irreducible representations. Okay, the first one is the following. If you see, first of all, let me remind you that gamma mu nu here, when I write here gamma mu nu, this is anti-symmetric in mu and nu. Therefore, this d mu and nu can be anti-symmetrized, and you can write this as 1/2 f mu nu, where f mu nu is the anti-symmetric expression, d mu and nu minus d mu and nu. Okay, so there is f mu nu into the game. Okay, therefore, if you select lambda, f mu nu, and d, okay, and you look at how lambda, d, and f mu nu transform, you immediately see that delta lambda transforms in f mu nu and d does not talk to anything else. Delta d transforms into lambda and does not talk to anything else. If you, this is the exercise that you have to do. If you look for the transformation of f mu nu, which can be got from here, from delta mu, you will see that this term goes away, and again you get that delta f mu nu is expressed in terms of lambda. Okay, so it shouldn't be very difficult for you to realize that these three fields are definitely a sub-representation, and they build up an irreducible representation. The second irreducible representation is given by, sorry, this is what people call dV, is given by m, n, lambda minus I d slash chi, d mu a mu, d plus box c. This is a little bit more involved. This is what people call dV. Okay, this is probably a little bit more, you need sort of more longer thinking. but you can realize that in fact these components transform among themselves using the transformations that I wrote here. Okay.
There is a question.
Yeah. Oh.
On the chat.
Why V is called the scalar multiplet contains also vector field? Because the super multiplet is a scalar. Okay, now because now, yeah, the question is, you know, kind of name relies on the nature of V, which in turn relies on the nature of the lowest component. The lowest component is a scalar, so that's why we call the multiplet scalar. You produce a vector, but when you apply supersymmetry transformation starting from a scalar, okay? But this is just notation, names. Okay, I have another observation regarding the scalar multiplet, which is the following. This is another exercise that you can try. So let me first write exercise 1. Prove that dV and dV are in fact representations. Okay, and the other exercise is the following. If I set dV equal to 0, setting dV equal to 0, it means that you set m n, and this expression dV mu equal to 0, and this expression equal to 0, okay? What we are left with of course, we are left with a shorter multiplet, which contains only, look, if we go back, okay, you have to take this multiplet, you set m equal to 0, n equal to 0, lambda equal to the slash chi, therefore lambda and chi are no longer independent. Then you impose the mu a mu equal to 0, which means that not all the 4 components of a mu are at this point independent. And then you have a constraint on D plus box C equal to 0, therefore also D is no longer independent. Good. So what you are left with in terms of independent components is the following. You have C, one of the 2 Majorana spinors, chi, and a mu, which is, however, constrained by the condition d mu and mu equal to 0. Good. This is what people call the linear multiplet. Okay. Just in case you come across to some books or some review paper where they talk about the linear multiplet. Okay, this is something that I would like you to check. Well, it's really very easy. You can check how the linear multiplet transforms under SUSY transformation. Right. SUSY transformations for L. Okay. Finally, if instead we set dV equal to 0, dV equal to 0 means that we set lambda equal to 0, D equal to 0, and F mu equal to 0. It means that A mu is a pure gauge. In this case, if we write, first of all, we can write this implies F mu equal to 0, which implies that I can always write A nu as the nu of some A. I called it A. Okay, it's the derivative of a scalar. Okay, therefore we are left with the following independent components: A, which is this new scalar that I introduced here. Then we have C, chi, M, and N. And if you arrange things suitably, in particular, you will arrange A and C into a field phi as the it's a real and imaginary component of a new field phi. You arrange M and N into the real and the imaginary components of a new field, scalar field F, chi is chi. What we obtain is basically, we are back to the chiral. We obtain a chiral multiplet. Okay. Okay, this is, and you can check that this is true. This is what I wanted to say about the field realization of representations. Is that clear enough? I hope. We have talked up to now about the representations built up in terms of states, but of course, dealing with quantum field theory, we prefer to realize representations, which means supermultiplets in terms of a bunch of fields. Okay. Now, the point is that I'm going to choose to change completely subject. I don't know whether it makes sense to do it now, because what I want to introduce at this point is n equal to 1 superspace formalism. I don't know. I might start recalling how one usually define Poincaré Minkowski space. And then next time we generalize to superspace, but I should know how much you know about ordinary Minkowski. Let me just say something, and then you will tell me whether next time I have to go through it more carefully. Okay, so what I have in mind, so we eventually, my goal is to introduce n equal to 1 superspace, but to begin with, I want to review Minkowski space as a coset. Okay, so what I'm going to hopefully review, I don't know if you know these things already, is that, well, first of all, you should remind yourself about the definition of coset. Coset, which is in general written in this way, where G is a Lie group, H is a subgroup, and this notation means that the coset is the set of equivalence classes defined in terms of the following equivalence relation. So if I take G and G prime being two elements of the group G, we claim that G is equivalent to G prime. Okay, if G prime can be written as G compose H for an H in big H. Okay, so the two elements are equivalent if they differ by the right multiplication by an element of the subgroup H. This is why we write the coset this way. This is what we call the left coset. And basically, the coset is the set of equivalent classes built up in this way. Of course, for each equivalent class, you can pick up a representative. Plus, we pick up a representative. Let me call it G bar. In fact, any other element of this equivalence class will be of the form G equal to G bar composed H for an H in a big H. Okay, this is the general definition of coset. Why I'm going to tell you that? Because now this is a claim that I don't know whether you are familiar with or not. My claim is that Minkowski space is in one-to-one correspondence with the coset Poincaré, so ISO 1,3. This is the group G, coset Lorentz. This is Poincaré cosets Lorentz. Okay. Are you familiar? You can write the answer in the chat. Well, let's do it this way. People who are familiar could avoid answering. Please just let me know if there is anybody who is not familiar with this construction. Okay. Last thing that I can tell you is that, as I said already, for every yeah, so probably. Okay, there are people who are not familiar. Okay, so next time I will focus on it in more details. But let me just conclude the picture. In which sense there is a one-to-one correspondence with Minkowski? Because now we can pick up a generic representative of the coset. We can define a representative for each equivalence class, which is of the form L of x equal to e to the I x mu p mu, where p mu are the generators of translations. Okay. X mu are in principle a set of 4 parameters, 4 real parameters, but what I, of course, like to do now is to identify x mu with point coordinates in Minkowski. Okay, so in this way, I have a one-to-one correspondence between each point of Minkowski space-time and the representative of equivalence classes. Okay, then we can make some operations, but at this point I have to stop. And okay, so I will go through it a little bit in details next time. But please, next time, let me start from here. So I will give it for granted that you learned already that, you can represent Minkowski as the coset Poincaré, coset Lorentz.